Welcome to a brand new episode of Machine Learning Made Simple. Here we unravel the enchantment behind machine learning, demystifying all the technical jargon. I'm your host, Shogato, and I'm here to chat with you about the revolutionary changes unfolding right before our eyes in the tech world. Let's dive in. Welcome back to another episode of Machine Learning Made Simple. In today's episode, we're going to talk about large language models and the evolution of large language models and the agentic models that are happening, breakthroughs that happened in the past few months, and we're going to talk about that. And we know we talked about a lot of reinforcement learning because we are trying to do those things in parallel, because most of the developments in the AI world is coming in three different directions. But we're going to keep away quantum technology away for a while, but most of the AI breakthroughs are coming in the large language model and the agentic framework, and also in the reinforcement learning paradigm. So we are working both of them in tandem. So we go through some reinforcement learning methods in few episodes, and then we switch back to the large language models. In today's episode, we're going to talk about the recent breakthroughs that happen in the large language model world. A lot of things happens as the hardware are ramping up, as there are more resources available. Then the researchers are able to come up with new techniques and new cutting edge applications of the large language models. So for now, all the multimodal large language models were focused on audio processing and text processing and image processing. Mostly when we talk about multimodal large language models, usually people think that, okay, in addition to text, it can also handle images. So if we upload an image of a cow grazing to a ChatGPT like large language model or Anthropic or whatever multimodal model we have, let's say Llama 3.2, and ask it describe that image, then the model will describe the image in detail that the cow is grazing on a meadow. And if we ask more detail, then it can say what breed of cow it is and what kind of grass it is, for example, what color of the sky it is, are there any clouds. It can get as detailed as it's needed. So that's pure multimodality, where the large language model can not only handle text, but it can also handle other modes of communication like images and also audio. When we talk about, let's say, chatting with a large language model like ChatGPT has a feature which we can have a full-blown conversation with the model, where we can just talk and converse normally in whatever language we prefer to use, English, French, whatever, and instead of typing in, we can just converse. And in fact, Sam Altman is actually very proud of that feature, that we can directly converse with the model like a human being, like a personal assistant. And I also feel that is one of the greatest features to come out, but the only problem is that it's very limited. And if you have used it for a while, you know that after some time ChatGPT is going to cut you off. Let's say you chatted for half an hour, then it'll cut you off or go to a lower level large language model. So if you're using 4.0, then it'll probably go down to 3.5. So what is the answer to these? So what is the answer to the rate limitations that we experience with this multimodal model? Because we love to chat with these models online. So the answer is pretty simple and straightforward. Host your own multimodal language models locally and use a web interface to chat with it. Of course, you have to write your own app for that to use. And of course, given all those Pythagora and other code generators that are available out there, then writing your own app is pretty straightforward. Yes, you can't get too detailed, but a rudimentary app anyone can cook up right now. So it's pretty simple. You host your own large language model, load up. Let's say you use Ollama. Ollama would be the best option here, because you're not interacting with it directly with a UI. You're interacting using voice modalities. So in that case, the best option would be to spin up a large language model server like Ollama server, and then spin up a Llama 3.2 multimodal model and serve it over your LAN, and then connect it with some other device which can ingest that. And also parallelly, you have to start another service which can encode and decode audio. So you might have a Whisper model that can decode any language, English, French, whatever you're speaking, on the fly, and then send that as a text to a large language model. Or some of your large language model can do it directly. Llama 3.2 can do it directly. So that's where you can interact with very little latency and of course no rate limitation. But most people, I'm guessing, will not be able to do that because there are a lot of moving parts. You have to have a Llama server, a local LLM server, you have to have Whisper running, which can at real-time encode and decode speech, and you also have to have an app which can interact with these API backends. So these are not for the faint of the heart, but it's okay. I mean, if you are happy to use ChatGPT, then go ahead and use it. But if you're unsatisfied with that, at some point we do need to set up these kind of things, especially for small startups and enterprises, small businesses. They need to set up these APIs, these backend systems, so that they don't get rate limited. At least their users do not get rate limited. If we're serving as a startup, serving that functionality where our users can chat with it. For example, I know of a healthcare startup which provides this service to its users, where the users can chat with an AI agent in a conversational tone to have mental health resources available to them. For example, if someone is suffering from depression, they can chat with an agent like a real human being. So that saves a lot of resources. Having a human being interact and help someone with mental health issues is very costly. Replacing the human being with AI agents is substantially cheaper. However, it's not as cheap as we think, but the hardware resources, the cost of renting those hardware resources are coming down sharply. So hosting these are pretty simple. So that's a very good use case for using a multimodal capable AI agent, where we run an AI agent which is fine-tuned to provide very good mental health resources or help with mental health, and have be a resource to people suffering from mental health. And then also it has the ability to have interactions and judge personality and all those things from previous interactions, and all have those APIs there which can encode and decode speech and audio on the fly in real time, and then have a large language model perform those resource intensive tasks, like giving advice to people suffering from mental health issues. And all of these can be done in a pipeline very simply. Now, that being said, this needs a little bit of expertise to be set up. People would just have ChatGPT or Anthropic code generators at their disposal might not be able to set it up, because code generators are here and they're here to stay, and they're going to replace many people. What they are not going to replace are architects, software architects. So the plumbing that's required to connect these APIs, those backends, to create those database connections, those still cannot be fully done by the code generators. So you still need human beings, experts, to perform those tasks. So I always say that be someone who is expert in those software architectures, then your job is pretty much safe for a little bit, because the code generators still cannot do those integrations. So if we need to integrate AWS with, let's say, Azure, because let's say our LLM, our OpenAI is hosted on Azure, but our data is stored in AWS, because AWS has excellent auditing capabilities. If you want to be regulatory compliant to regulatory bodies, and you have to keep an audit trail, AWS is one of the best services to have and host your data, because the data management, data versioning, metadata curating, or keeping an audit trail is done from the base level in AWS. And this is one of the best things I've seen. Azure also has that, but I have seen AWS's auditing capabilities is far superior to most of the others. So now let's keep talking about the multimodal model. So what happened? So one of the major breakthroughs that happened is the advent of video large language model, or VLLMs. So these are fully multimodal models now, so it can even look into videos, and which was a hard task before. It's very resource intensive, because videos, imagine if you have to describe what is going on in a video, we not only have to analyze each frame, and there might be 25 frames per second, we also have to see the progression of the events. So there is also a time component that's added, so there is an extra complexity added to the whole process of ingestion. One of the holy grails of any kind of video descriptive agent is that it should be able to identify key events. For example, if there is a soccer match going on, it should be able to describe when and identify when a goal is scored, or if there is a football match going on, like a rugby or a football match going on, again they need to be able to identify key events. So when there is a touchdown that happened, when there is a foul that is called, or all these key events it needs to identify, because then if we need an automated process so that the network can run ads, so if there is a free airtime, you don't want dead airspace, you don't want to fill that airspace, those prime time, with ads. So all those all those media platforms which host all these real live events like games, matches, their holy grail is to find an AI system which can identify these key events. And they have been working on this for a while, and I know for a fact, and I have talked with a few of them, and I know many of them have those AI systems where they have developed their own fine-tuned versions where it can go and detect these key events. And there are a few ways they can detect key events. Is one by, of course, analyzing the audio. So if the audience is screaming goal, then probably in a soccer match a goal has been scored. So that's one way to tag those set of frames. There's a goal has been scored, so okay, cut to ad. So that might be a triggering event. Or if there's a touchdown, suddenly the volume will go up because everyone would be celebrating. So those are key events, looking for volume amplification, specific keywords in audio. And now video processing is more challenging. However, previously people had been using YOLO, you only look once, or DETR, or any kind of object recognition to see if a specific set of players have performed a specific set of actions. So if it's following the object, let's say an object which is the ball in the soccer field, if it goes to the goalpost and it can identify that path that the ball that it's tracking has gone into the net, then so this is a very complex set of things that it needs to do. It first needs to track, and it has to make sure that in that space that the object ball has entered the object net. Then it will trigger that event. It can be done, but it will require some amount of hard coding those special instructions, and it will require some skills in order to do that. And it can be done. It can be done very well. So now that being said, now what does these new set of video language models do? These video language models will completely make those hard-coded rules obsolete, because these video language models can now identify those key events without additional training or additional rules that needs to be added manually right now. For now, let's say a media management company is adding those rules by hand in order to trigger the ads. So okay, the goal is scored. So what are the events that will lead up to us? They have to look at all edge cases because the camera is also moving. So depending on all those edge cases and all those rules needs to be executed to trigger that specific events to start the ad sequence. So now these video language models can completely bypass all that and just detect that keyframe where the goal is scored. So if you give it a video and says like, okay, show me where the goal is scored, then it can probably go directly to that key event. Or it can just, if you give it the video and it says like localize all video segments containing the given action baseball pitch, then you know when the baseball was pitched, and it can detect it almost immediately. Now whether this is real time or not, it's still debatable. It's probably not real time yet, but for replays, this would make post-processing very simple. For example, if we have a video of a baseball match, for example, and then we need to cut at places where specific events happen. Let's say we want to run an ad every time a baseball pitch happens. So it can automatically detect that keyframe and cut it and splice it and insert the ad there and close it. So imagine how fast post-processing would be with these video language models. Let's take another use case. Let's say we are national park and we are trying to figure out how many tigers are crossing a specific zone. So there are a couple of ways of doing it. We can always run YOLO and just count, and there are codes for that. Or we can use this video language model and it says like every time a tiger passes, take a screenshot. So that's amazing. So that then we can save those screenshots, and then we can see if they are the same tiger. See, this is a different workflow than the YOLO workflow for object detection. For YOLO workflow for object detection, it's just going to detect tigers. If the same tiger goes past the camera 10 times, then it's going to count 10 tigers, right? So it's not giving us an accurate count of tigers. However, with this new workflow, if we are using a video language model to identify tigers, then it's taking a screenshot, then it can take all those screenshots and make sure that the screenshots of the tigers are unique. So let's say the same tiger goes past 10 times, and then another tiger goes past. So there are 11 screenshots, and then this language model can identify that 10 out of those 11s are the images, screenshots of the same tiger. So it will only count 2 tigers which has passed before the webcam, and then we have a better accurate estimate of how many tigers there are. So that's really going to improve our workflow. But that being said, these problems were known before, this overcounting issue with YOLO. So what to do in those cases? So in those cases, there are workarounds. If we still don't have access to these video language models, because these video language models are 75 GBs, it's not an easy thing to run or cheap thing to run, but they will become better as they become quantized by the community. But for now, these video large language models are pretty big. So what are the options right now if we do not have access to the video large language model? Of course, run YOLO, count using YOLO. Now, the only way to solve the problem of overcounting is to take screenshots at regular intervals. So let's say 5-10 seconds, you keep taking screenshots. Now you pass them through a fine-tuned image detector which can identify, okay, so these are different. So it will give an identification score and confidence level that these set of tigers looks like the picture of the same tiger. So if there are like 11 pictures, let's say there are 200 screenshots now, because it's taking screenshots every 20 seconds or 5 seconds intervals or whatever the frequency is. Then from all the screenshots, it can see, let's say, okay, there are, let's say 200 or 300 screenshots that are taken. Of them, it can say with some confidence that there are only like 2 or 3 tigers, because most of them are screenshots of the same tiger from different angles. So that will avoid, so which means we have to do a little bit of extra work to get around that problem of overcounting with the object detection models. Now let's talk about this paper called Tarsier 2. This is an advanced large vision large language model with detailed video description to comprehensive video understanding. These are called LVLM, large vision language model. So this is not the first of the kind that they try to develop, and we'll talk about all the challenges in training these kind of models and building these kind of models. But let's first quickly visit some of the parameters that make these models great. So one of the great things about this model is that now, like we described before, that these models can describe videos. Previously, those models could only describe images, of course, and audio ingestion is always there. Now these video models can now describe videos. So if we give a video of, let's say, a baseball match and give an instruction, detect and localize all the video segments containing the given action baseball pitch, and provide the outputs using start at end timestamp. So what it does, it analyzes the entire video of the baseball match, and every time there is a pitch, it can get the starting location and a starting time frame and the ending time frame of that. So if someone pitches a baseball, then that segment can be clipped out. That segment can be clipped out. So if a baseball coach is looking to use this, all they have to do is dump that video into the video large language model, and give that instruction, and out comes all the timestamps. And then you take those timestamps and feed it in a, let's say, bash script, which can use FFmpeg or some other kind of command line tool to strip out all those time frames. Now let's take another use case. So let's say we feed in a video and I give the instruction, create a video description by outlining each frame thoroughly. Use simple words and concise sentences. Also include observations about the video's artistic style. And the output from the video large language model can come out as frame 1. A white dog with goggles and green helmet sits on a red object against a blue sky. Frame 2, the same dog still sitting with a slightly different background. Frame 3, a red plane flies over a bridge with a train below. Frame 4, the plane continues to fly over the bridge, moving to the right. Frame 5, the plane is further to the right, closing on the bridge. Frame 6, so it's going frame by frame by frame. And frame 8, it says the dog is now leaning forward, looking determined. Frame 6, a pink dog with a purple scarf on the red plane with the white dog in the distance. So you see, it can detect and describe frame by frame, which is amazing. Now, what is the advantage of using this kind of capability? So we can take a video and get an entire video description, and then we know what's going on in it. So we can create subtitles from it. So if the subtitles is already not provided, we can create an audio description for visually impaired, and it can describe and then transcribe that audio and create an audio using an audio generator from text, and then people who are visually challenged can actually enjoy a movie just by the audio descriptions of each frame. So it will take a little bit longer, but it can be done. So that's one of the great use cases. And also that video can, for example, a video feed from a security camera can be ingested, and then it can be converted to text, which will make detection much easier. Let's take a use case. Let's say you are creating an intrusion detection system for your own home. It's a DEI project. So previously what we had to do is we have to take the video feed, send it to some cloud platform, and then have it analyzed for anomalies or changes. We have to use object detector like YOLO or DETR to see if there's some specific objects were detected, especially late at night. Let's say everyone is sleeping between midnight and let's say 5 o'clock in the morning. That's when the code is looking for any changes in the scenery. If the scenery changes or any other objects like human beings are detected, then it will trigger a warning that there might be an intruder. So now with this new capability of video large language models, what can happen is that the entire stream, the stream that's going through the streaming processor on your cloud provider, can now detect frame by frame and analyze it and create that into text. So every frame that is streaming from your motion detecting camera can now feed and go through those system, which has a backend of a video large language model, and the video large language model can take each frame from the streaming video from your camera, from your security camera, and then convert that into text. Now that text can be ingested by another LLM, which can see that, okay, so nothing is happening. It is getting the same reading for every frame, but then it sees something. Let's say there is a motion detection and there is a cat coming into the frame. So the video description says there's a cat walking across. So that video, the LLM ingests that, and it's like, okay, a cat is not going to be a burglar. So now maybe there is another event where the stream goes through your processor, and the video large language model now detects someone who looks like a burglar, is walking around your outside patio door and behaving in a funny manner. In frame by frame, it's sending those textual descriptions to your threat detection large language model, and your threat detection large language model is seeing that the threat is escalating every second because the person is moving around and behaving in a very suspicious manner. So the large language model, after a few seconds of observations on and escalating threat levels, it's going to trigger that warning and send out the warning to the different channels. It's a text. It might also send it to the relevant authorities, and that will be a very robust system that we can create and deploy for home. And this has huge implications in terms of personal security. Now let's talk about a little bit of the technical details of this large language model. So one of the main challenges of the large language model is its training. It's so resource intensive. Any training of any machine learning model or large language model involves huge amounts of curated data sets. And you can imagine for the video data sets that needs to be curated would be massive, and hand curation is almost a no-go. So synthetic data is what people mostly rely on. So the way they train is they use some kind of reinforcement learning as the regular DPO training, but the main challenge is still the synthetic data set. Even generating the synthetic data set is quite challenging, and we'll talk about that more when we discuss the Lava paper. The Lava video was previously the state-of-the-art model, but that being said, both the video Lava model and the Tarsier group, they work together to solve this problem, and they do talk about that in their paper, that they worked and collaborated together. Now that being said, this Tarsier 2 model is released by ByteDance. So if you're familiar with TikTok, you know what ByteDance is. ByteDance is the parent company for TikTok. So now the question is, since this is a foreign-owned entity, are you going to use this model? Yes, you can use the model. Just use it in an air gap fashion, or don't use sensitive videos. For example, don't use your own personal videos that you don't want anyone to see for analysis with these models. For now, this is the only open source model that actually is SOTA that's out there for video language understanding that we can use. So we are pretty much out of options, so we have to use it. So, but just make sure that you can use it in an air gap fashion if you have a large enough GPU. So if you don't have a 80 GB or larger GPU cluster, then you are kind of out of luck using it. You have to use it online. And in that case, you cannot really air gap this. So in that case, just exercise a little bit of caution. Don't use videos that you don't want to be passed on to some other external entity. So do not use in a governmental setting, do not use it in an enterprise setting, do not use for any kind of sensitive material. For now, keep it simple. Now let's talk about the Video Lava model. This is the precursor to the Tarsier 2 model that we just talked about. The Video Lava model, essentially these groups kind of collaborated together. Tarsier group from ByteDance and the Video Lava model group, they actually collaborated. And one of the things that they recognized is that the main challenges of training this video language model is the data set. It's very resource intensive, manual labor intensive to create those data sets in order to train these models effectively. Now, if you look at the technical details of how they trained or created or curated the data set, so you'll find similarities between when people were trying to train those multimodal models for image recognition, especially the VQA model. So the way those VQA models are trained is that used to be trained is like we have an image and then we give it two options and ask you to select the right option. So let's say we give it the image, we give the model, show the image, the model of a parrot, for example, and ask the question, identify this bird. I give you two options. It's a parrot or it's a crow. And then the model has to select whether it's a parrot or a crow. And we also have answers for these kind of labeled pairs of question answers. We also have, so this is our X, this is our input, and we also have output labels, which is the same thing as the Iris data set, only slightly more complicated. So now the output, which we know the answer to, it's a parrot, and then we give the answer back, and then we find the loss function. So if the model outputs crow, for example, for the visual question answering, after seeing a parrot, it outputs crow, for example, so then it's wrong. Then the loss function will match it with the corresponding label, which is a parrot, and see, okay, it's a parrot, but it is labeled as a crow by the machine learning model, so the loss function is high, and then that will guide the gradient of the stochastic gradient descent towards the correct answer or the correct representation of the model. So the visual question answering was created in this manner. You have an image and question answer pair, and then there you have the labels, and then the loss function allows the model to give an answer. Then the loss function detects how well the model did. If the model did poorly, it will be forcibly pushed in a direction where it becomes more and more correct. It will iteratively improve the model in a step-by-step fashion. The same idea here, they also do the same thing. They have videos. So instead of visual question answering, they have a video question answering. So they have a video, then ask a few questions. They have answer A and answer B, and the model has to choose one of the answers by looking at the video. So there are other things that they also mentioned. There's like previously it was thought that in order to have a video understanding of the multimodal capabilities of large language models, it's only sufficient to extract each frame and then just describe the frame. So essentially it's just reducing the complexity of the time-like axis to just the complexity of describing an image. For example, if we extract one single frame and describe that, and that's sufficient. But these authors actually responsibly said that is not the case, because just describing a single frame doesn't have a holistic view of the entire sequence of frames that's happening. If we take the image of a person standing in front of a store and not have the information of subsequent frames where the person throws a stone through the glass window of the store, then we don't know. We'll just see a person standing in front of a store. The language model doesn't see those subsequent frames. So only by mashing together all the subsequent frames into one complete picture, then only the language model can understand that what is going on. It can accurately describe the sequence of events, and that is important. So what the author says is that what they do is that they take as many sequence of frames as the video memory allows, packs them into a latent representation and give the combined latent representation to the video model, which can now make those inferences. Of course, these are tagged. The sequence of frames, let's say it takes like 60, 70 frames, whatever that's allowed by the video memory, is fed into the latent representation, and then it's annotated by the authors manually is what is happening. Let's say someone throws a rock at the store window, and those sequence of frames that describe it is cut out, fed into the language model, and also tagged with that annotation by the authors by hand. Is like the person is throwing rock and breaking the window of a store. So a lot of hard work goes into this, training these models. So when these models eventually become mainstream and are used in products like security cameras and early detection systems, we probably will start using them without realizing how much hard work went into building those models. In the same way, I don't realize how much hard work goes into all those mechanics of cars. Like even the car window probably has like hundreds of moving pieces. People over the years painstakingly probably have assimilated all those components, and we use it without even thinking about it. And then the same thing will happen. There's a lot of hard work is going into building these models, which will eventually be productionalized and made into enterprise products like security cams, live security cams, which can detect live events and describe live events and announce it. Like something is a burglary is ongoing, it can directly send that feed to a nearby police station and announces like a burglary is in progress. By looking at the video feed, you should go there immediately. So the store manager doesn't even need to hit a panic button or anything. So if there's a burglar or intrusion in any home, they can have those systems which can automatically detect and relay those messages to the nearby authorities, the closest authorities, almost instantaneously, so that and then they can respond almost as quickly as possible. So one last thing I'll say about the Video Lava paper is that their main contribution was automated caption generation. Usually when we generate captions, we have the transcript, we have the audio, we take the audio and use Whisper or something else to create the transcription, and then we use that to generate captions. Now captions are not easy because you have to have time by time frames in order to generate them. In fact, there is a model which can generate those captions right now from videos, but this kind of contribution by Lava Video is that they can look at frames and can generate captions on the fly without audio, which is amazing. Until next week, stay curious, stay critical, and keep asking those important questions. See you next week. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.